Okay, so it says find the volume of a solution when 0.30 grams of calcium hydroxide is dissolved to form a 0.20 molar solution. So start with the things we know. And we're going to end up with a 0.20 molar solution. Question says find the volume of the solution. So when you're looking for volume of a solution, what you're going to be doing we're going to start with our number here, 0.30 grams. And then we have to change it to moles. We didn't want it in terms of grams per liter or anything like that. So we're going to have to change it to moles. I gave everybody the AP periodic table, right? It has pretty specific numbers. Those are the ones we're going to want to get used to. So let's see, let's find this one. If you were to stick with the 74.096 for the intermediate stuff, it's really not going to change your answer. It might change it by a couple thousandths. AP is pretty well prepared to deal with it. There's only one question on the whole test that grades significant figures. So out of the whole second half of the test, there's only one question where it matters, and you'll know it when you see it because we'll talk about it ahead of time. So those of you who are math students who like to record every single digit that the calculator says, you're not going to get counted off for that as far as AP is concerned. I'm not overly strict on it in here, but I really don't like to see like 10 decimals after the number. So keep it under control. So I'm going to use my 74.10. And we're looking for volume. What's my next relationship? Does anybody know? We have a conversion. It just doesn't look like a conversion. This 0.20 is actually moles per 1 liter. And to fit it into this calculation, we're going to flip it upside down. And we end up with liters, which is the volume that we want. And we just run our calculation. Let's see, for in the name of time, I've already got it here. So if you put it in your calculator, you should end up with 0.02. And it's in terms of liters. If you look over here, we were given numbers with how many significant figures? They have 2. And so we're going to want 2 in our answer, and it ends up being 0.020. Your calculator will probably leave off that last 0, so it'll be up to us to put it in there. This next one, find the volume of 0.30 grams silicon dioxide gas. And for those of you that watched the video, make a divide here. You'll see that we had one that was volume of CO2 at STP. At STP means that it was automatically 22.4 liters per mole. But here we're given different conditions. We have 30 degrees Celsius and we have 400 torrs. So when you have a gas that's not at STP, we will not use 22.4. So let me write it over here. I'm going to put a big red X through it. If it's not at STP, this is not a thing. So we have to use something that maybe we're not extremely familiar with. It's the ideal gas law. And that is PV equals nRT. We want to know volume, so we divide both sides by P. So here's the formula, and we just have to figure out how things are going to fit into it. So as a refresher, N is number of moles. So I'll write these down. If you don't have space, you don't have to write them down. R is the gas constant. I'm just going to write a constant. T is temperature. One thing about temperature, it has to be in Kelvin. And of course, P is pressure. So just a preview of this question, this number in terms of grams, we're going to need it to be moles. There's a conversion that we have to do. We're just planning this out right now. 30 degrees Celsius, that's our temperature. We're going to have to change it to Kelvin. 400 torrs is pressure. And before we change it, we're going to look at the gas constants to see how it's going to fit. So take out your AP formula sheet. I can probably make this easy on you, because each of you want two of these things. One for the periodic table, one for the formula sheet. Make it easier to find. Yeah. Everybody. Had the school buy me 200. This formula sheet is probably going to make an appearance almost every day, which is why it's going to be so important we can find it. This is the 2019 version of the formula sheet. Since then, they have made one change. They added a formula. We won't need to even talk about that formula until about February. Okay, so we want to know something about gas constants. So if you look on the back side of this formula sheet, there's a section that says gases, liquids, and solutions. They try to separate this to make it make sense. Yeah, these are super static. They're hard to mess with. So while you're messing with that, I'm going to look through the gas constants. I'll read them to you. So the back page in the section on gases, liquids, and solutions, right side, about middle of the page. It says gas constant R, and it gives us three values. There's one in terms of joules per mole per Kelvin. There's one in terms of liters times atmospheres per mole per Kelvin. And here we have one that says liters times torrs per mole per Kelvin. That's the one we're going to want. It has moles, it has Kelvin, most importantly, it has torrs. So we won't have to convert this to anything else. You can put your calculations really however you want, but we can fit all of this into the formula. So for our section for N, for moles, we can do our 0.30 grams and change it to moles as long as we know the molar mass. So using our official AP periodic table, we've got 32.06 plus 16 plus 16. See if I need a review on molar masses. If you don't want to speak on the tape, you can just raise your hand. Maybe I'll put it in the tutoring videos anyway. Okay, so all of this comprises our value for N. Grams divided by grams makes it moles. Then our gas constant. Are we able to look at our formula sheet now? Gas constant R, it's the third one. 62.36 liters times torrs per mole per Kelvin. I realize it's a pain to write units, but it's really important. Every year I get sent to a conference for AP chemistry so I can learn all the new stuff and how they're grading it and whatever. And the thing they tell me every year is this student probably could have figured it out. They did it almost right, but they didn't include units. And so they ended up missing one little piece because something got moved around. Temperature. It's in terms of Kelvin. Let's do our temperature conversion down here. Celsius to Kelvin. You take your Celsius number, and the formula is actually on here. Let's find it. I think it's on the front. It is on the back. Okay, yeah. So on the left side, Kelvin equals Celsius plus 273. There's a lot of students who will mess up this conversion just because they didn't bother to double check themselves on the formula sheet. Celsius plus 273 means that this is 303 Kelvin. 303 Kelvin. For the pressure on the bottom, since we have torrs in our gas constant, we'll just stick in that 400 torrs. And before we go too much further, this is the point where putting units into your formula is going to make a big difference. There's a ton of numbers here. So I just want to make sure that everything's going to cancel. So grams are done, moles, there's per mole, Kelvin, per Kelvin, torrs, and we're left with liters. And that's a good sign if all of your units cancel out to leave you a volume when you're looking for volume. That's what we need. So take a look here, and you should come up with 0.22 liters. So you're going to type all of it in and stop in the middle.
Sorry.
Okay. So volume is 0.22 liters under these conditions, which were not STP. Here's probably a note. On the AP exam, it's very rarely going to be 22.4. In the multiple choice section, it might show up once, but in the second half of the test where we do stuff more like this, it's never going to be at STP. So this number probably not going to be showing its face. Number 4, find the density in grams per liter of each of the samples. For aqueous solutions, assume that the volume of solutes is negligible and that the density of water is 1.0 grams per milliliter. Okay, so it says CO2 at STP. And we want this in terms of grams per liter. They didn't even give us anything. Anybody have any thoughts? Take 10 seconds to think about it, everybody. That's what we're looking at. Is that what you're thinking? Okay, so we don't have any specific numbers, but we know how everything relates to moles. So let's just imagine for a second that we had 1 mole. Even if we had half a mole, it would eventually be the same ratio. So CO2 has a certain molar mass. We've got 12.01, 12.01, 16 times 2. This is the molar mass. So density equals here's grams per mole. And then the second one we said was 1 mole per 22.4 liters, which is essentially the same as saying 44.01 divided by 22.4. Moles will cancel and we get, it's almost approximately half, or 2, 1.96 grams per liter. Questions on that one? You just want to try this on your own?
Do we assume the second one is not STP?
It's a solid. Okay, so for the second one, and I don't know how yours differs from mine off the top of my head, it actually gives us a density, so I should probably lead with that. 6.85 grams per cubic centimeter. I have a feeling that whatever book they were using was on their desk and they had to look it up, which is why it's not written down. This is something you would find in the back of your textbook. It's got about, 150 pages of references, stuff like this. So we have the density of the solid, and we just want to convert it to grams per liter. So some things that are not on the AP formula sheet. 1 cubic centimeter is 1 milliliter. They're not going to tell you that. And 1,000 milliliters in a liter. They're not going to tell you that one either. Those are implied that we know it. This is something that either a question will give you or maybe a reference table will be provided. Okay, so the third one, 0.20 molar calcium hydroxide. And here's something interesting about the way the AP format works. So one like this, you might have to look up the page to find actual numbers. A lot of times they'll give you a number up here, and then when you get down here, expect you to use the number that's way up at the top. Sometimes you got to look around the page. So we want density in terms of grams per liter, which is mass divided by volume. So we had the mass of calcium hydroxide, and this is where it comes into play. They told us 0.3 grams last time, and that's going to be the number for pretty much all of these whenever it comes up. 0.30 grams. Remember what the volume was? Look up the page. So we're rolling back to number 3, the third part of number 3. We found the volume of the solution when 0.30 grams of calcium hydroxide formed a 0.20 molar solution. And we found that the volume was 0.020 liters. So let's stick in some numbers. Volume goes on the bottom. Now, it's not as cut and dry as saying the mass of calcium hydroxide divided by the volume of the solution. So there's a lot of water in here. So we need to know the mass of the water. Here's how we're going to do it. We have 0.02 liters. What all do we know? Let's change it to milliliters. Do we know the relationship between grams and milliliters? something that we should probably just try to remember in our head, the density of pure water. Yeah, it's 1-to-1. And it actually even tells us in the number 4 main question, assume the density of water is 1 gram per milliliter. So 1 gram per milliliter. This is one of those questions where we already had all the numbers, but it was kind of a hunt. So here we end up with 20 grams. So when we're talking about the density of this solution, it's the mass of the calcium hydroxide plus the mass of the water. And here we're going to have a number in grams per liter. It ends up being 1,020 grams per liter. The pure water itself, if the density is 1 gram per milliliter, would be 1,000 grams per liter. So most of this is water. Only a very small portion of it is the calcium hydroxide. Give this last one a try. Sulfur dioxide gas, 30 Celsius, 400 torrs. We want to know the density. How are we doing? Are we making progress? See if I start a paper. Okay, so see varying levels of progress. Let's figure out this SO2 gas that is not at STP, the mass of this gas. This is one of those things where we just have to look up the page. What was the mass of SO2? We have a number in grams given to us in a question, 0.30 grams. In that same question, in part 3, we found the volume of this gas, and it was 0.22 liters. So we put this in our calculator, and this will give us the number that we're looking for, and it's 1.4 grams per liter. easier than we tried to make it. Sometimes our default setting in chemistry is to think that they're going to be more complicated. And actually with AP exam, part of the reason it's so difficult is because it's simpler than we think it is. Like a lot of times when I'm first taking one of these exams like you do, I'll do it really in a complicated way, and then I'll look at the answer key and it'll be something like this, where there was like two numbers and you divide it. So it's just our instinct, all of us, to make it a little more complicated. Okay, so let's look at, I won't do all the rest of these questions. Let's do maybe one of them. Let's try number 6. For your e-learning for this class tomorrow, the stuff the other class is doing today, hopefully they watch the video before they attempt the question, because if not, I foresee a lot of writing and erasing. It's easy in a way. It only took me about 2 minutes and I didn't look at the answer key, but I was kind of expecting it not to be as complicated as it looks. They gave us a lot of space here, and really we could have made it difficult. So let's write down some of the basics of what's going on. 32.57 gram sample of copper metal. And what it tells us is that copper metal is burned in oxygen. So here's copper. Burning in oxygen means this is a basic combustion type reaction. And the mass of the product was found to be 36.67 grams. So I'm going to write 36.67 grams. I'm just going to call it product. First question, describe what is happening on the molecular level in this process. So describe what is happening. This is one of these things that AP will try to ask you to do. Describe what's going on. And try to do more than just a rephrasing of the question. They don't really like that. On the molecular level, we have, so let's just say solid copper atoms combining with gaseous oxygen molecules. You don't always have to be this specific with AP, but I'm trying to get us in the mindset of thinking about what's going on with a little bit more detail. So use this to come up with a strategy for the problem. So does anybody actually know the formula of product? No, I don't either. Here's what the question is doing. We're going to have to figure it out probably. We'll see what's going on. So here's what we know. We know how much copper there is. We know how much of this compound that there is. The difference between the two, what is it? Difference between these two numbers, oxygen gas. So what's the difference between these two numbers? Can you type it in? 4.1? Okay. So 4.1 grams of oxygen gas. So we know something else here. So since we know these masses, we can come up with maybe an empirical formula. And I know both of your classes did empirical formulas. I don't think either one had anything get in the way of that. Shut down or not. So here's what we have to do when we're talking about copper. These things have to be in terms of moles. We can't very well compare copper in grams with oxygen in grams. We have a unit for that. So we have to convert to moles. 32.57 grams. And our formula sheet says 63.55. On the wall says 63.564. Pretty close. Can I get somebody to type that in for me? And the other one, oxygen gas, 4.10 grams. Let's change this to oxygen atoms. What did we get for the top one? Anybody got it?
Point 5125.
Okay. What about the oxygen? Anybody got that one? 0.25. Are you rounding, or was that the exact number?
0.2506.
Okay, thanks.
There's more numbers.
No, we'll stick with 4. Everything has 4 except for this one, and we calculated that one. So we're going to stick with 4. Okay. So we have about half a mole of copper. We have about 1/4 of a mole of oxygen. Here's how it's going to work. We're just going to compare them. Remember what we did last year or 2 years ago? Divide by the smallest one. So we end up with 1 on the oxygen. We end up with, it's going to be 2 for the copper. So the empirical formula of this, Cu2, last part of it says write the balanced equation for the chemical process. States are important. It's going to be a solid. All right, last thing I'm going to say before I turn the tape off. We just balanced this equation. On the AP exam this year, there was one where it gave you the equation, it gave you everything. All you had to do was balance it. It left little blanks everywhere. And so it looked like this, blank, blank, blank. And I think they were even labeled A, B, and C. And over on the left side, it said A equals, B equals, and C equals. Okay? So the balancing part was easy. Most of the students were able to balance it appropriately. The problem came from moving these numbers to over here. What's A? What's C? And then guess what? About half of the people missed it because they put a 0 here. Because we do implied ones in chemistry all the time, and they forgot that a blank was an implied 1 and put a 0. And missed this whole question because of a transcription error. So be careful with that. This is an implied 1, it's not a 0.